Our talk is this decays of correlations for Anosov flows. So first of all, so given a compact remaining manifold M, so flow G from M to itself is called an Anosov flow. If there is a continuous splitting of the tangent space as a sum of three bundles. So one is this ES and one is this N, which is the flow direction, and one is this EU. And the ES is contracted, uniformly contracted by this time-one map of the flow. And then EU is also uniformly expanded by this time-one map of the flow. So we say that this ES is the stable bundle and the EU is the unstable bundle. So it is known that for any Anosov flow, so this ES and the EU integrate to stable foliation and unstable foliation respectively, but they don't have to be jointly integrable. So the topological and the statistical properties of Anosov flow were studied by many authors. So there, I listed some of the authors which, the earliest name of these lines of research. So there are Anosov, Bowen, Margulis, Plant, Ratner, Rel, Sinai, and Smell, and etc. So for transitive Anosov flows, the following theorem is well known. So there is this so-called Anosov alternative. So transitive Anosov flow is topologically mixing if and only if the stable and unstable foliations are not jointly integrable. So you cannot find a foliation which is saturized by both this stable foliation and unstable foliation. So we say that GT is topologically mixing if for any, this is the definition of topological mixing, if for any open sets A and B, and for all sufficiently large T, we have this GTA intersect GTB non-trivially. So it is also important to study this major theoretical mixing. So for Anosov flow, GT for an Hölder function F, there is a unique measure which maximizes quantity. This quantity may look a bit strange at first sight, but it appears naturally in many of these applications. So it is called the equilibrium measure for G with potential F. So when F equals to 0, mu is the entropy maximizing measure, just by this definition. So when F equals to this is something that we call geometric potential. So mu is the so-called Sinai-Rel-Bowen measure. So it is the limit of this Birkhoff sum of this push forward of this Lebesgue measure. So in particular, when GT is volume preserving, then mu is the volume. So these are the two most important equilibrium measures according to what I read in the literature. So when GT is topologically mixing, then GT is also topologically mixing with respect to any equilibrium measure with Hölder potential. I remember this is a result of Bowen and Rel in 75. So namely, by topologically mixing with respect to measure, I mean that for any two functions a, b, a square integral function, so this we have this convergence. So a gt times b, and the average of that tends to this. So people are interested in the speed of the convergence when a, b are Hölder functions. So usually when you study this speed of convergence, you have to put some regularity for these functions. So they have the following conjecture by Bowen and Rel. So when GT is topologically mixing, then GT is exponentially mixing with respect to Hölder functions and equilibrium measures with Hölder potentials. By exponentially mixing, I mean that this convergence is exponentially fast. So there are some previous progress on this conjecture. So first of all, we have this, I think the first breakthrough is made by Dogopiat. So he proved that you can have this exponential mixing when these ES and EU are of class C1, and the exponential mixing is measured for SRB measure. I just mean this the measure with the geometric potential. Oh, but I cannot.
But there's a certain spot where
Okay. So maybe can I?
yeah. But I would have to plug that in for you.
No, but this is not working.
I'm using it right now. You should be able to use that. Right is advanced.
Okay, thank you. Okay, so it is true when these both stable and unstable distributions are of class C1 for SRB measures, and for all equilibrium measures when this dimension is 1. So actually in the proof, Dockerbell only needs certain regularity for the equilibrium measure, so I think it's called the Federer property for the equilibrium measure. So when dimension of this equals to 1, then all equilibrium measures satisfy this property. And then there's a result of Liravani. It shows that when GT preserve a contact form, then you have this exponential mixing with respect to volume. So then we have this result of 2G. So he showed that in dimension 3. By that I mean the dimension of the manifold is 3. This GT preserved, and when GT preserved the volume form, then there is an open and dense set of volume preserving Anosov flow, for which you have exponential mixing with respect to the volume form only. Okay, and then there is a result of Bartley and Wall. They show that when this ES, the stable distribution is C1 plus epsilon, then they can show this for SRB measure. So I suspect that, I didn't look at their paper very carefully, but I suspect their method also works for equilibrium measure when this dimension equals to 1. I mean, under this Federer property. So usually this EU and ES, they do not need to be smooth. So they are always a holder, but in many cases they are strictly holder, and exponent can be actually small. So this is they're like a sequence of work studied by Plant, and then Plant is for 3D volume preserving case, and then there are Hasselblad and Wilkinson. They show this exponent can be actually small. But that's for higher dimension. So in 3D, I don't know whether or not, I'm not familiar with the, whether or not very low regularity is possible. Okay, so this is what I did last year, the last semester with 2G. So we show that there's an open and dense set of C-infinity 3-dimensional Anosov flow for which this Bovin-Reals conjecture holds. So very recently we started to think that our method also works for, so we have this open and dense condition. But very recently we started to look at this original problem, which asks for exponential mixing under only topological mixing. And I have to check some details in this Bartley and Wall, but very likely that we can solve it under this mixing condition. So there is another. So there is besides this topological genericity condition, there's another natural notion for genericity. Is the so-called prevalence. This is a notion invented by Hunt, Sawyer, and York in 80 or something. So let B be a Banach space. We say that subset is psi if there is a complex supported measure mu on a probability measure on B, so that this thing holds. So probability is called prevalence if the set of elements without this property is shy. So we find out that actually for this prevalence, the question for exponential mixing is much easier. So for any CR Anosov flow, exponential mixing is prevalent among its CR time reparameterizations. So in particular, you can show that so this conjecture holds for, this exponential mixing holds for a dense set of these Anosov flows. Okay, so that's all.